We've used the term workspace in this and several previous modules. Now it's time to define those a little more carefully and see how they play a role in how functions are called. Up till now, we've informally used the word workspace to refer to any collection of variables that all live in the same place. We've used the commands who and whose, which give information about the variables in that current workspace. In the future, we're going to focus on two important types of workspaces. The workspace we're familiar with, which is visible from the Matlab prompt, is called the base workspace. In addition to that, each call to a function creates what's called a function instance workspace. These are created when a function is called, and they disappear when the function completes executing all of its code. We'll see in a few modules that functions can be called recursively. Hence, there can exist many workspace instances of the same function. These workspaces should all be considered isolated and non-interacting. Variables with the same name but different values can exist in these different workspaces. There's also a global workspace, which we won't be working with very much, but you may come in contact with that as you further your study and use of Matlab and other programming languages. Now let's see what happens when a function is called and how workspaces come into existence and ultimately disappear. Here's the MATLAB prompt, and there's an empty base workspace which we'll start to fill by creating variables. Let's create a variable v1, and in the base workspace a variable v1 exists. It's now 3 by 1. Another line of code creates another 3 by 1 variable v2. Now let's call the function vecop. Notice that a vecop function instance workspace is created, and the arguments from the base workspace, v1 and v2, are passed into this function instance workspace, and they appear as the input arguments in the function declaration line v and w. Now this function starts executing. The first line of code creates a 1 by 1 variable dp that exists in the function instance workspace. The second line of code initializes a 3 by 1 array cp for the cross product, and then several lines of code fill that, changing the value of cp but not changing what's in the workspace, which is 4 variables. Now the function is done, and the next thing that must happen is the function must exit and return the output arguments. There, dp is being returned to the variable a, and cp is being returned to the variable b. The function and its workspace disappears, and the variables a and b are created in the base workspace. So to summarize, input arguments are passed into the function, code in the function body creates the output variables, and the output variables are passed back to the caller, which in this case is the base workspace. Let's look at this simple function call again, using two commands, whose and dbstack, which when executed gives a list of all the other currently executing functions. We'll learn more about dbstack as we move forward through the course, but for now that's a good enough explanation of what it does. I'll go through these commands fairly quickly here on the slides, and then we'll move to MATLAB and actually do it. So we'll start with a clear to clear the workspace, a whose to see that the workspace is empty, create the two variables, and run a whose again to see that they are in the workspace. Then we'll do a dbstack to see that no functions are running right now. We're just in the command window. That will return nothing. Finally, we'll call vecop v. The v just indicates that this is a slightly different function than vecop, with some printouts and calls to who and dbstack interlaced within the code. Here it is. It starts, and it will print out that we're in vecop v, and then it will make a call to whose and a call to dbstack. We will see the function instance workspace with that whose call. Then we'll create the dot product and perform another display stating that we're in vecop v after the dot product calculation, and again run a whose and a dbstack. We'll create the cross product vector, do a whose and dbstack there. Finally, we'll compute the cross product calculations and declare that we are after the cross product calculations, and then do a who and dbstack, and then leaving vecop v. At that point, control will return to the command window, and we'll do a whos there and a dbstack to finish the example. Okay, let's try this in Matlab. Let's open the editor and look at VecOpV. I want to point out that when we run who's and dbstack, we'll always do some sort of a display followed by the who's followed by the dbstack. That's always the order in which we do things. Display who's dbstack, display who's dbstack, and then finally a display at the end. Okay, let's try this and see what we get. We'll start by clearing, and who's shows that nothing is in the workspace. Let's create V1 and V2. Now who's shows that the workspace has two variables, V1 and V2. dbstack returns nothing, indicating that no functions are running. We'll call VecOpV. This will produce quite a lot of printout and return command to the command window. We'll scroll back through the printout and discuss each term. Let's scroll back and see what happened. Here was the call. The first thing was the display, which printed in VecOpV, and then it ran a who's command. The who's shows the function workspace. There are two variables, V and W. Let's look at the code again. Those should be the variables V and W at this point. We're right here in the code. This is the output of dbstack, which says we're on line 3 of the function VecOpV. Next, there's a display after the dot product has been computed, a display and a who's and a dbstack. Here's the display, and now the who's indicates 3 variables in the function instance workspace, the dp, which has just been calculated. Finally, the dbstack says that we're at line 6 in VecOpV. Confirm that. That's where we are, line 6. Next, the cross product vector is created and another display and dbstack. Cross product, there's the display. The who's shows 4 variables now in the function instance workspace, and dbstack indicates at line 9 of VecOpV. Finally, the calculations occur and another display and who's are run. This should look very similar, just that we'll be at a different line. The workspace appears to be the same, still 4 variables, and at line 14. Lastly, there's the leaving VecOpV display, which is shown right here. We're back in the workspace. Let's remember what function was called to do this. The arguments were A, B, V1, and V2. Now when we do a who's here, we should see V1 and V2 still, and A and B, as they were returned as output arguments. The variables dp, cp, lowercase v, and lowercase w were local to the function VecOpV. They were displayed when we ran who's inside the function. We were examining the function instance workspace, but they're not displayed here. The function instance workspace is in fact gone. We can run dbstack to see that no functions are executing. We'll continue with more complicated examples illustrating these ideas. Next, let's see the behavior of Matlab when we call a function with fewer output arguments than are defined in the function declaration line. We'll continue to use the vecop file for this example. Let's create 2 variables. They appear in the base workspace. And then a call to vecop with only 1 output argument. As we learned previously, the input arguments are copied into the function instance workspace, creating 2 variables there, whose names correspond to the input argument list in the function declaration line. Now, all the code executes. dp is computed, cp is allocated, cp is filled with the correct values, even though the caller only requested 1 output argument. So what happens on return? As the function exits, the first argument is passed back to the caller, so q will have the value of the dot product. The function exits, the function instance workspace disappears, and q appears back in the base workspace. It's 1 by 1 because it represents the dot product. In general, the behavior is that functions may be called with fewer output arguments than are defined in the function declaration line. The function executes all the code, even if that involves computing arguments which are not going to be passed back, and then it returns the arguments, filling the caller's argument list from left to right. So in this case, there were 2 output arguments defined in vecop, the dot product and the cross product. The dot product is the first output argument, therefore that is what is returned in the variable q. What about the composition of function calls? So one function call as an input argument to another function call. Function calls can be composed. In this expression, a call to func1 becomes the second input argument in a call to func2. What is this equivalent to? First, call func1 with one output argument, regardless of how many output arguments func1 is defined with. Then, take that output argument and use that as a second argument to the call to func2. The message from this slide is that the original line behaves exactly as if func1 is called with one output argument, regardless of how many output arguments are defined in the func1 function. Then, that one output argument simply replaces the expression in the subsequent call to func2. We use this a lot, and you already have used this earlier in the class.